So hi everyone. In the previous video, we have discussed about the implementation of semaphores. And semaphores implementation deals with two atomic standard operations, wait and signal, wherein if we want to acquire a certain resource, we use the wait operation. But if we want to release a resource, we use the signal operation. So this is the source code for the wait operation, as you can see. So it has the parameter S, or the semaphore S, okay, that indicates the number of resources that is available. So it has a while loop, as you can see, that checks whether there is a certain resource that is available. So if this is less than or equal to 0, then that means that there is no resource available, and this must be stuck in a loop. So this will continually loop until such time that the S is no longer less than or equal to 0, which means that there is already a resource available, and then it can break out of the loop. Okay, so if a certain process wants to enter its critical section and this while loop evaluates to true, that means that some other process is still using that shared resource and is in the critical section, so we have to wait. All right, so it means that the certain process that is waiting is essentially called in the busy waiting state. So the continual looping is actually a problem in real multi-programming system, wherein a single CPU core is shared among many processes. So the busy waiting also wastes CPU cycles that some other process might be able to use productively. Okay, so this is actually called as the spin lock, because the process spins while waiting for the lock to become available. Okay, so now instead of using the wait and signal, we make use of the block and wake up operations instead. Okay, so it means that rather than engaging in the busy waiting, the process can choose to suspend itself. So the suspend operation places a process into a waiting queue, and that is associated with the semaphore. And the state of the process is switched then into a waiting state. Okay, so as I said, in order to overcome the problem of the busy waiting, instead of the wait and signal, we can make use of the concept of block and wake up operations. So we have a struct here, assuming implemented in C. So we have a struct na variable, struct semaphore, that has these two attributes value. So the value of the semaphore, so how many resources are there, and the list that refers to the waiting list that is associated with the semaphore. So what it means is, assuming that we have several processes that are wanting to enter their critical section or using that certain shared resource. So if we no longer have any resource available, then rather than putting this P4 in continuous looping and ending up wasting the CPU cycles, we put it into the waiting queue that is associated with the semaphore instead. So P4 suspends itself and puts itself in the waiting queue. Okay, so then the control is transferred to the CPU scheduler, which selects another process to execute. Okay, so with each semaphore, there is an associated waiting queue. And each entry in a waiting queue has two data items, the value of type integer and the pointer to the next record in the list. So this refers to those definitions refer to these variables, the value and the list. Okay, and we have two operations, block and wake up. So when we say block, we place a certain process invoking this operation on the appropriate waiting queue. So assuming this P4 was placed into the waiting queue P4, so that happened because of the block operation that we did. Now we also have the wake up operation, wherein we remove one process in the waiting queue and place it in the ready queue. So assuming there is already a resource that is available, so we remove one of the processes from this waiting queue, and then we put it back into the ready queue. Now, the control is transferred into the CPU scheduler that chooses which of these processes will be executed first. Okay, so this is the semaphore implementation with no busy waiting. So we still have the wait and the signal, but we make use of the block and wake up operations. All right. So, and then we also have the ready queue as well as the waiting queue that is associated with the semaphore. So for the wait na operation, so it still has the semaphore na pointers here, and essentially we are going to decrease or decrement the value first. Okay, decrement the value of S. So that means that we decrease the number of resources that is available. And if the S na value is less than 0, which means that there is no longer resources available, then instead of putting that certain process into the wait to a endless na loop, we add this process into the waiting queue instead. And we block that process. So the P4 suspends itself. Okay. And the signal operation instead is that, you remember, if we want to use signal, that means that we are releasing a certain resource. So that means that there will be more available na resources. So essentially, in the signal, we increment the value of the S na value, okay, indicating that there is more resource available. And if the S value is less than or equal to 0, then we are going to remove a process P. We are going to remove the process P from the S list. So we are going to remove that process from the waiting list, transfer it into the ready queue, and wake up that process. So essentially, the P4 is no longer suspended and it may now execute. Okay, and it is up to the CPU to choose which one of these processes to execute first. All right, so let's have an example. But before that, these are some of the reminders. The semaphore value may be negative. So depending on the number of processes that are waiting. So for example, if we only have if only have one resource available and we have 4 processes that are waiting, so it will be kept on decremented. Okay, so that means that the S may be negative. So its magnitude is the number of processes that is waiting on the semaphore, as I have discussed. So the list of waiting processes can be implemented by a link field in each process control block or PCB. So we can make use of pointers for this actually. So what it means is we are pointing to the process control block of each na process. Okay, so let's have an example. Assuming that we have 4 processes and we only have one shared na resource. Okay, and each na process wants to enter the critical na section. So what would happen then? So first is, let's say S1, process 1 wants to enter its critical section. So the value of S will be decremented. Okay, decremented first. And now, is S value less than 0? So it is false, since we have a 0 na resource. So that means that we are not going to add this P1 into the waiting queue. So we will just skip this process. Okay, and then now P2 also wants to enter the critical section, but it has to wait. Okay, so we decrement the value of S first. We decrement the value of S, and S is now equal to -1 from initially 0, right? So now, is S value less than 0 or is it negative? And it is true. So since this is true, we are going to add this process to the list that is associated to the semaphore or the waiting queue. We add P2 into the waiting queue and we block and we apply the block na operation. Okay, now P1 is done with its execution, so, or done with its critical na section, so it is now in the exit na section. And since nasa exit na siya, we are going to use the signal operation. And in the signal operation, we first increment the value of S by 1. So increment the value of S, so essentially adding 1 to S. So we have now 0. And is S value less than or equal to 0? So since this is true, so we are going to remove a process P from the waiting queue. Okay, so we remove the P2 from the waiting queue and we put it in the ready queue. Okay, we actually put it in the ready queue, assuming that the P2 was selected by the CPU and of course now in its critical na section. Okay, so yeah, that's it.